Hello everyone. In this video we are going to take a look how to use tools from the Scraiber olivine segmentation software programmatically. So the Scraiber project has been founded by the NFTI for Earth, and the main idea of it is to provide access to scientific pipeline which only has been used for olivine segmentation and was accessible only by a small number of people, to make it accessible to more people and to make it reusable. So if you want to work with it, especially with in a programmatical way using Python, first of all you have to clone the Scraiber GitHub repository, where in the examples folder you can find this processing Jupyter notebook with the examples. And so what we do, the first step, we import all the things we need, and mainly for the processing of the BCF files of the backscattered electron images and the segmentation of the olivine within it, we need this package or this folder accessible in our Jupyter notebook. So we execute this line of code, and if we do so, now we can start with a comparison. So if we are processing backscattered electron images, this tool is bases or uses as input BCF files. Those are files created by the Bruker electron microscopy software. And to be able to work with it, we have to convert them in a more useful format, also stitch them. So normally they're in a tiles format where several images are taken for a single phenocrypt. To convert a BCF file into a more usable format like TIFF format, we can use this method bcf2tiff.bcf2tiff. As input, it takes path to a BCF file, and the second parameter, the path where the converted file should be stored. In our case, we don't want to convert just one file, but all the BCF files contained within the test data BCF folder, and therefore we use this globe call to get all the paths, and then with a for loop we iterate through these files and convert all of them into TIFF files. We can take a look into this folder, the test data folder. Here we have our BCF files which we use for the comparison, and the output is the TIFF folder. In there are several TIFF files which are representing actually the data we have exported from the BCF files. We have like element maps for the iron, magnesium, and others, those elements which are typical for the identification of the olivine, and also we have for each file this YAML containing the meta information extracted from the BCF file. The YAML files are easily human readable or also automatically readable, and then easy to use within the Python environment. Okay, now we have exported the TIFF images, and what we need to combine them into the into a single image. This we are doing using simple stitching from the mimlim folder, and now we say simple stitching dot stitch auto and provide the path where the TIFF files are stored. We do it, and we have here the size of the pixels and also the size of the offset, like the overlay between single tiles, which can be configured on the Brooker software, and the result is stored in TIFF stitch. Let's take a look into it. And we have first of all the YAML files copied there, not to lose meta information, and also we have like the visualization of the backscattered electron microscope data and the original raw data, which is again hard to visualize. Okay, so we have the stitched image of the backscattered electron microscope, and now we want to apply our deep learning tool to segment those olivines within this data. This can be done by importing the segment module and then by providing the path to the TIFF file from the backscattered electron data, and also we provide like the output folder for it. In this case, this is also the stitched folder. So let's import it, execute it. So what happens there, it is a large image. It can be processed in a single phase, therefore it is split it into overlapping parts and then processed by the semantic segmentation script. And this is the outcome. And now when we have the segmentation, what we can do, we can identify single isolated crystals, so perform a connected component analysis, and also calculate some statistics based on it. To do so, we import a section analysis, and then we execute section analysis.analyze with and provides a stitched folder. If we now take a look at it, we see this analysis folder which has been generated by the method, and we have like two folders. Full analysis results are like CSV files containing statistical information, and within the catalog row we have a catalog of the crystals typified with provided certain types. So for example, SUP are the subphenocryst, V stands for reversed zonation of the crystals, and no zonation or other zonation are stored within this folder. We see in the like the single crystals, we can take a look at the visualization of them, and like reverse zonation has this part. Okay, so thank you very much for your time. If you want to contribute to this project or have suggestions how it can be improved, you can also write an issue at the GitLab project of this it's a GitLab site of this project. It's Git of the RWTH Aachen, NFDI for us group, and especially Scraiber. Okay, thank you very much, and bye.